Okay, so today is about lecture number 4. So we're going to continue on the second law of thermodynamics, right? Let me recap what I explained to you last time, right? About the second law of thermodynamics. So So we have learned that second law of thermodynamics is something to do with the word right. This word right. This is statement about impossibility, right? Like you cannot build a perfect machine or heat machine, right? Something like that, or heat pump, that kind of thing. And we know that that is the most efficient heat engine, which is actually the Carnot one. Okay, that what we have learned last time. So today we're going to capture this statement. Oh, sorry. Yeah. Okay. ขอบคุณครับเนี่ยครับ Okay. So we're going to capture this into physical quantity okay, known as entropy. Okay, so this is the highlight guide for today, the entropy. Okay. So let's consider, okay, an expansion of ideal gas, okay, which is actually, we know that actually this is a reversible process through isothermal okay. So you're going to have this of course PV diagram right here, and you have a line which is, we know that this is an isotherm, right? So suppose that this is the initial point and this is the final point. So what is happened, because the isotherm is, suppose that this is with temp T, okay? Temperature. Temperature T, which is along this line. The temperature is constant, right? So it means that this process you have to, at the beginning, so suppose this is the chamber of your gas, okay? And then, so the gas is localized in this portion, right, which is Vi. Okay. Okay. Vi. So what we're going to do is that we're going to put this chamber into a hot plate, hot body with temp T, right? So this is nothing but a reservoir. Okay? Yep, with temperature T. Here. So it means that heat will getting into the chamber, and the gas will be expand, right? So it means that at the end, so you're going to have this picture. Suppose that I can draw things perfectly. I mean, this is exactly the same portion. Okay. So your gas expand, and then so this is a new volume, which is actually Vs here, with of course with a new pressure, of course, but you have to keep in mind that this still your system still attached with the hot body here. Okay, so if you look at this, so we find that the gas expand, then you can compute from the first law. Okay, we find that this one. Right here. Since we're working with the ideal gas, but the ideal gas, you have this relation, right? So then you can solve for P in this way, right? And so you will get that okay, you will get this relation, and you rearrange it a little bit, you will find that so this means that the ratio of this change of the volume, right? And the volume here is proportional of this quantity. Okay. So here is a thing. A gas occupy more space. I mean, in this way, it's more volume, right? After the expansion. Okay. So in this sense, so we can say like in the in not the right perfectly okay, but you can say that this gives you something like more this order, but I put this, yeah, because it's kind of you start with this bit, right, of space, and then your molecule occupy of this, and then when it expand you get something bigger and then more randomly, yeah. And of course you can say that this is more randomness, but again this you have to be careful with this, okay, on position, okay, of each of the molecule of the gas, okay. Thus this fraction fractional of volume change here is a measure of the increase in this order I again put this because as well you probably know that actually on the social media I mentioned a lot that actually entropy is not really a measure of this order of the system, right? But in this sense we can start to with the thing that actually you can say that, oh, okay, with more space it's more randomness, right? Something like that. But you will see the true meaning of entropy later, okay? But in this sense, you can say that. And as I mentioned, this is which is actually and is proportional. It is proportional to this quantity. Okay. As you could see from this equation, right? So with this kind of way of thinking, we going to introduce quantity this one. Okay. Where S is called entropy of the system and the S is nothing but the change of entropy. Okay. All right. Okay. So by working with this very simple system, we get this new quantity, okay, that we call entropy, okay. Now, what we are going to look next is for the cyclic process, okay. Cyclic process. I would say reversible. Okay, reversible cyclic process, like we do have in the Carnot, right? One. You have two isotherm here, which is Tr and Th here, and you have your system start with this and then expand along this and then expand further and then let's see, and then get back here, right? So the heat coming in here, the heat coming in, and some of the heat spilled out, right? And the area under this loop is nothing but the work done by the engine, right? Okay. So from this, what we have that actually we learned from last term that actually, right, yeah, the work done is different, right, between heat coming out and leaving the system. Okay, so along then, throughout the process, okay, I mean from A to B and to C to D and back to A here. This is adiabatic process, right? Processes, so no heat transfer, right? So it means that so in this bit and this bit there is no change of the entropy, right? BC delta S dA, right? Because there is no change of entropy. So the change of entropy you will get from this and this, I mean thermal expansion and thermal contraction, okay? So what you get, the change of entropy is from this and this, which is actually T, yeah. Okay. So so you can see that actually the change of the entropy throughout this expansion is positive, right? Because heat adding up into the system, right? And then if you look at this, like in this picture, the volume of the cylinder is expanding, right? While this one, the heat has been taken out, right? And then it's the volume is contract or suppressed, and then yeah, that is the reason why it gets negative, right? Okay. Next, since entropy is a state function, then we have that actually right here, cyclic process, right? Yeah. So it means that it is state function, the difference between the entropy it depends on the initial and the final point. And if the initial and the final point are the same point, then there is no change. So this is consequently, so you will get that this H on, oh sorry, this should be H here, and that should be L here, sorry. Okay. Or you get this relation out. Yeah.
Why we don't consider entropy in the another process why we only consider in the thermal process, isothermal process?
Oh, interesting. Because why do we have that? Because let me think about that. Your question. Yeah, it's that is actually very interesting. Like if we do consider in this adiabatic process, then we could not define anything. Yeah, because there is no heat flowing out and flowing in. So then, yeah, you cannot get this kind of thing relation here. So actually, the reason we look at this kind of at a starting point, because we would like to, I think we want to show that actually this bit going to affect on this how much on that kind of thing, right? Okay, with this constant temperature that actually your system that are attached on with the surrounding. Okay. I'm not sure. I'm not sure that the answer that you want, but yeah, well, yeah, interesting. Let me think about this, and then I will answer you next time. Why do we have to do with only thermal expansion? Okay, so now we have this kind of scheme, this type of relation for that cyclic here. Then for any cyclic process like this here. So it means that you can, of course, this is the cyclic one, right? And then you can say that actually there is a thermal I might not good at drawing here, but I believe kind of makes sense. Okay. Support. Okay. Something like this. So this is all the different thermal line, the isotherm lines actually, right? So it means that you can do the approximation like what we did here. So you need to add this 2 bit, right? So what we did is we could do things like this and like this, okay? And then you will get this portion at that this can be approximately to be that can be approximate as the that one as the previous one, previous example. Oh, I should not use this color because it's very difficult to see. So it means that in this cycle you will get that this one, right? Okay. I mean, so you will get heat coming in here and going out there, right? It means that if you look at this, I mean, the process here. So there will be heat getting in here from this loop, right? So you get something like you have to add them up, right? So this could give you so the total change is small. Okay, I put the small because this is small one, right? Small. This is total you have to add all the small one okay, in this way, which it look very simple because suppose that you have n cycle right here. So it means that so you're going to have summation here of this here, right? And so with the limit n, right? So you will get kind of the closed loop integration, right, of this, which is actually 0. This is for any reversible process. Okay. Then, so from this, then we now define entropy chain from I to F. Okay, it's going to be this. Okay, this is a definition of entropy chain. So, well, as we put the assumption here, right here, that actually the entropy is the state function. It means that is somehow there is a feature of it, right? Path independent feature, right here. So it means that if you have the initial point and the final point here, so you go along this part 1, right, and this part 2. So it means that the entropy chain of part 1 is going to be the same of part 2, right? Okay. That is thing. So before we move to the case of a reversible process, let me recap you again. For any reversible process, the entropy chain is 0. All right, okay. Then you get this yeah, I would say, okay. This is the highlight of this one. So next we're going to consider for irreversible. Okay. Okay. To get the condition of the entropy change for this reversible process, we're going to look at the heat engine. Okay, we're calling the Carnot theorem. Right. You know that and engine that operate between two temp. This is temperature, okay? It's my shorthand. Is less efficient than the Carnot one. Okay, this is what we have actually we proved last time, right? And so suppose again that we have, let me draw here. This is a hot reservoir, and this is the cold reservoir. All right, and then you have Carnot engine, and you have heat flow in and flow out, and then you have work done here. And so we should I can extend. Okay, and then this is engine. With Q arm. Okay, this one. I mean, so this is a reversible engine. I mean, this one. Okay, this is the Carnot one, which is very ideal one, right? This is the ideal one, is the most efficient. So what we have last time, that we know that the efficiency of the kernel is greater than, right, then so the efficiency of the kernel, right, is greater, and so this going to give you this relation. Right. Okay. Then, so you get that okay, this one. And so by actually we proved that efficiency of the Carnot engine actually proportional to the ratio of the temperature, right? So you can just put there. Okay. So finally, what you have is that the portion of heat of the reversible engine is this inequality, right? Yes. And I put here. Let me finish this. And so then you rewrite. Sorry. Rewrite. Okay. So you will get that this okay. It's not difficult to see that. So or now I mean here we put the absolute here because we take care about the minus sign and the plus sign. But if we don't care about the minus sign and plus sign, we just put QL over TC plus, yeah, that. We can do this. Okay. So this or it means that so it's less than 0 for a reversible. Okay. So in order to get this inequality, you have to draw the, I mean, this is the irreversible cyclic process, and then you break it down to small pieces, and you will get this anyway. Okay, as we did in the irreversible case. But I'm very lazy to do that. Then I just take it a big step. I mean, here, right? I claim, okay. I mean, you have to, but I just too lazy. I just claim that actually, if you do this, you're going to get that. Okay. So here, then let me conclude, and then I'm going to take a 5-minute break. เพราะไอปวดฉี่มากเลย Okay, so now we have this so if you include equality sign, you will get that if in this situation, this is for reversible, and of course, this is for reversible. This is known as the clauses inequality. Okay. Okay, clauses. Okay, inequality. Now, so I stop here for take a break, and then I will be back.
Me too.
Okay.
Okay.
Continue.
Yes,
So here we get this inequality now. So next, let's consider this, the combination of the process between reversible and irreversible one. So now, next, we consider suppose, okay, there's A, B. So I get part 1, which is I would like to use the yellow line to indicate that actually this is irreversible. Okay. And so I have another 2 part, which is I call 2, and both of them reversible. Okay. All right. Okay. So now we consider the loop AB, which is, it depends on which way that you're going to. So if you start from here and you go along the part 1 and then you come back with the part 2, you will get a loop, this. So I label this, so you will get I, right, plus, which is less than 0, okay? But, however, we also have a closed loop for this one. Right, yeah. I love this. So you could go with the part 2 first then, okay? And then oh no, sorry. You come back with the part 3, which is actually equal to 0 because this is the irreversible loop or cyclic, right? Then oh, this is what? Oh, this is 2. Okay. So from here, so you can use this, you can plug this equation into this one. You will get so we get which is this one, okay? Or here. And I shall define this is entropy change, right? Because you have to remember we define here the entropy change from the feature that actually we consider the reversible process, right? Right. And then this is the reason why we need this bit in order to define the entropy change between the 2 points on that. So I would say the entropy change is it greater than this, right? That is a thing that we get. Here, a reversible part. Okay? Okay. But for the reversible part, you will get that equation. Okay? But for the irreversible part, you will get that inequality. Okay? Is that clear? Okay, good. So if part I, okay, is an adiabatic, I mean that so no heat transfer in and out, right? This one. Meaning that it is an isolated from the surrounding, right? Because there is no exchange of the heat with the surrounding. This is the definition of isolated system, right? Then the entropy change, which is this one, and you could see that this, I mean, the system for, let me summarize, for isolated system, okay, the entropy will increase, okay, increase, okay, if the system change under a reversible process, but for the reversible process is going to be zero, no change, right? Then, so isolated notation for okay. So now then what we could summarize here. This is the highlight now. Okay. It means that for so what we have now is that the entropy change will be this inequality. And entropy change will remain the same or increase for isolated system. Okay. So it remains the same in the case that actually for the reversible process, but for the irreversible process, you're going to get bigger entropy. Okay. So remark here. Let me put the remark here. The entropy change can be negative if the system exchange the heat with the surrounding, and of course this is not isolated system. Okay, then you cannot apply this rule, right? If you want to apply the rule that this would be the second law of thermodynamics. Okay, in the version of entropy. Okay, so if this is your system, right, and this is a surrounding, indicate that actually the heat flow out from your system to the surrounding, right? I mean, the change of entropy starting with the change would be greater than 0, right? Okay, but you say that, oh, this is my conflict with this, the second law of thermodynamics. Conflict with the second law? That is the question, right? The answer, no, right? Because it is just a part of bigger system which means this bigger system is called universe. In this context, in the thermodynamic context. So the universe is, you have taking into account the surrounding and the system. So in this context, it means that universe is the change of entropy of the system plus the change of entropy of the surrounding. Okay, which always greater or equal to 0, then you could say that actually this universe is kind of the isolated system now. And then you can, it's still true for the second law. So it means that actually if you have, it means that so it means that if this is your universe here, you have system 1, system 2, system 3, and it is surrounding, right? So I mean the entropy change of the universe is the change of S1 plus the change of S2 and plus the change of S3 must be greater than or equal to 0. But each of these bits can be positive or negative. But when you sum all them up, this equality must hold. That is the thing. So very good example, very simple example that I really like is like you have a hot reservoir or hot body with TH here, and then you attach with this with a cold body with TL here. Of course that you know that TH is greater than TL, right? Suppose that this is two of them are both reservoir, so the heat will flow in this direction, right? Can you compute the entropy change of this one and all of them together? Can you do it yourself now? Okay, please. I will leave this bit for you to show you calculation. It's not difficult, I think. No, actually. Why is 0? Why? The question is why it is 0. Can you prove that actually it's not 0? Can you prove with this? well, you have to use this condition. Yeah. ไอหิวข้าวแล้ว No pleasure. Take your time. ไอขอไปกินน้ำก่อนนะ Yeah. Just put your calculation on the board. Why not? And then let me see. Do it. Do it. Do it. Do it.
ติดก่อน
No need to do that. Mhm. Mhm. Okay. Correct. Yes, indeed. Yeah, that's correct. And this gives you the idea for like why heat to have to flow naturally from the hot body to the cold body, because the entropy change is increased, right, in this situation. This is a reversible process. Okay. Okay. Well, no. Actually, we assume that these two body as a reservoir. Then the temperature of this thing will be constant, and this thing also will be constant, right? It's going to be, I mean, if this is a two reservoir, the heat will flow law forever. This is so idealistic, but if you put a coffee mug, a very hot coffee mug on the table, and then you leave it for a while, and the temperature of the coffee mug will be the same with the environment. This is more like the same process, but it's much more complicated, like a coffee mug, right? Yeah. Okay. Very hot coffee mug, and you leave it on the table. And later, so this is like a room temperature, right? This is, and later, after you leave it for a while, so right, going to get to the equilibrium, and the heat heat will flow out right in this process in this way. Okay, so it means that for this particular system, heat cannot. This is not allowed, right? Because it's going to conflict with your calculation. Because if you allow heat to flow from the cold body to the hot body, this is going to be less than 0, which is actually conflict with the second law. So what I would like to say is that, again, this inequality indicate what can happen and cannot happen. Okay? Again, is about impossibility in this guy, all right? Impossibility. Again, but you capture this impossibility in terms of the mathematical equation here through the quantity that we call entropy. Okay. So that actually everything that happened in our daily life here had to follow this rule, otherwise it cannot be happen. Okay. So, and the thing is that is some part of you, what it might be some parts of your system actually entropy decrease. It means that it must be some other part of your system entropy have be increased in order to compensate and then to make sure this law holds. Okay. I'm not sure you get my point. Okay, good, very good. So like I mentioned a bit about like the history about black hole entropy, because at the beginning we don't really understand the thermodynamics property of the black hole, and so we say that okay, that is true, it's not. Should I mention now here, or should we finish the statistical mechanics first? Interesting. So the thing is that at the beginning, so if you consider the black hole and the rest of the universe, right, and then once the object or the mass or the anything, the matter get into the black hole, and then it just disappear out of our universe somehow. It means that somehow the entropy decrease, and then this kind of conflict with the second law of thermodynamics, then like a Hawking and Bekenstein, they think that actually the black hole itself has to be the entropy, and then when you add the entropy change of the black hole and the rest of the universe, right, and then the second law is holds. That is the reason why that this is the kind of system example. Okay, are we good here? All right, that kind of the second law. And so this is telling us that in the macroscopic point of view, which kind of process that allow to happen, okay, like this coffee mug, yeah, right. This is a very daily phenomenon, right, that you could encounter, you see in every day. Then I think then that's all for the second law, but actually there is more because okay, I'm going to talk about the meaning of the entropy in depth again when we get to the statistical mechanics, because there is a connection here. In this context we talking about the entropy change. We never compute the entropy. You know what I mean, right? We consider only the entropy change from this point. So this dot for those for the other point on your space of the thermodynamic space, right? That is the thing. All right. But anyway, when we look at thermodynamics, statistical mechanics, there is actually study the behavior of the microscopic things, and then there is a link that you're going to see beautifully with this kind of macroscopic thing. All right, so let me continue the third law. Third law states that the entropy of every system at absolute zero can always be taken to zero. So this is a statement of the second law. Then you can put this. Okay. So with this statement, okay. With this statement, one can define entropy of any state A like this, because you can say that actually you start from this state actually with zero temperature and you end up with this A, right? So you could, yeah, you could say that, oh, now we can compute the entropy at particular point on your space now, right? And so since Okay, we have this two relation. All right, then so the entropy could be now can be put and okay, in this way. So you need to do the integration of the t variable here, right? Then, so I would put the plum here because it's going to be in, this is the integration variable. Then. Here is a point. Classically, I emphasize this. Classically, the Cp and Cv are constant. What does it mean? It means that so you can pull out this Cv out of integration or Cp, right? So you're going to get some like Cp or Cv, right? And then you get 0 here. And then you see the problem. You see the problem. Here is a problem. Because this gives you infinity. So it means that, so, well, it doesn't make sense at all, right, to have this kind of equation, because you get infinity if you consider your system as a classical one, right here. Then it requires your C to proportional to the T to the power n at low temp. Okay. If you put this into your equation, you find that your S will be C0 over n Tn and okay, and greater than 0. And then once this 0 is okay now, right, there is no infinity. And this kind of feature of the kappa, I mean his capacity is not the classical feature, is a quantum one, like the Fermi gas. Fermi gas. Okay, we find that Cv is something like, we're going to deal with this later. Okay, but it's something, so it's proportional to T. You see? In this case, N equal to 1. This is the Fermi temperature, okay? Which we are going to talk about this later. Okay? Temperature. Okay, and then you know Fermi, right? Fermion, right? Yeah, it's the quantum gas, right? So, well, this kind of thing, this and this give us, in this sense, the third law. It's admission that the low temp world is not classical, but rather quantum. Okay, here is the point. So when you cool, when you cool down your system at very low temperature, the quantum effect will take over the classical one. Okay, that is the thing. And this is kind of one of the proof, right? That prove that statement. Okay, so let me summarize you, and then I think I stop. ไอหิวข้าว เป็นอาจารย์ที่แย่มากครับหิวข้าวก็หยุดแล้วพอแล้วโอเค so summarize so summary what we have learned so far the zero law. So we have temperature play a role, right? Play a role here, zero law, and you have you go to the first law. First law, you have internal energy, right? Internal energy, which it depends how you put heat and work into your system, right? Okay. And second law, you have entropy change. Okay, you have entropy change, this one, right? And the third law, you don't have anything, but you can say that at low temp, quantum will take over the classical. This is like a very short summary for this law as I give you example here. Okay, that would be we kind of finished more or less all the laws of thermodynamics, right? So the next topic is going to be thermodynamics potentials, which is we going classical. We're going to continue not next week, because next week we have workshop. Maybe I'm not sure. A week after, is that the New Year holiday, right?
Yeah.
If you're still around, then we can continue after. Okay, let okay. Otherwise, then this we can meet after the New Year. celebration. All right, okay, that's all for today, I believe, because if I start another topic, it's going to take the whole, I mean, maybe 2 hours to finish this. And I think it's better to stop here and find something to eat, okay? All right, okay. Hope you